the chair of our Vanatech Market Development Committee. He's going to give an update on IEC standardization efforts that occurred recently, as well as some further words on the vanadium market. So Terry, please take it away.
Very good, John. Can you just confirm you can hear me
I
okay?
can hear you fine.
Okay, great. I got a weak network here apparently, so if you can't hear me, wave your hand around a little bit. Anyway, appreciate the opportunity here to talk about what's going on in terms of electrolyte specification, standardization, and the vanadium market. So next slide, John. Right now, there's an effort within the International Electrochemical Commission, or the IEC, to develop a standard specification for electrolyte chemistry. And first few slides here, we'll just try and explain what IEC is. This is an organization for preparation and publication of international standards for all sorts of electrical and electronic related technologies. Next, please. The IEC operates on a global basis. Here you see a map that shows the full members in green, the associate members in light green, and affiliate countries in orange. And so this really is a global organization. Next, please. The IEC works through and if you want to participate in this discussion, we need to figure out which organization in your country is related with IEC for establishing experts to participate in this discussion. IEC is broken down into technical committees. The committee looking at the vanadium electrolyte is Technical Committee 21, Secondary Cells and Batteries. And within that technical committee, there's a number of joint working groups, and Joint Working Group 7 is developing the standard for flow battery systems for stationary applications. So this standard is going to speak to all issues about flow battery systems for stationary applications, not just electrolyte, but the physical side of the battery, safety issues, and really everything associated with the battery system. Next, please. There are 74 members in this joint working group, and there's a variety of countries here you can see are represented within the group. Next, please. Just to give you a snapshot of who's there in terms of companies here, if you look at the email addresses, you can probably sort out who's participated in the last meeting, which occurred in Tokyo back March 17th and 19th. I'll just say that one of the leading participants in this effort is the Fraunhofer Institute in Germany, and they've been very, very important in terms of putting forward ideas and trying to organize this discussion. Next, please. So why do we need to talk about a standard specification? First of all, the impurities in the electrolyte can affect the operation of the battery. And there's basically two types of impacts from the impurities, and we'll talk about that a little bit more in the next slide or two. The other important aspect of this effort is to try and create a global standard for electrolyte that all of the battery producers and electrolyte producers can rely on, and create really a common standard that will make sure the performance of the battery is adequate, but that we open that supply line up as much as possible. Looking forward at the demand for vanadium in these electrolytes, we're going to have to scale up vanadium production, and we want the specification to address those issues that are important in terms of performance, but at the same time creating an opportunity for a number of producers in the vanadium space to participate. And really the goal here is to try and create a market for a commodity, being electrolyte, that can be bought and sold and leased, as we just heard from the folks at Rocket Power. Next, please. This is a U.S. vanadium document that kind of looks at the impurities that typically are being called out in specifications. This is an agglomeration of about 17 different standards or specifications in the industry, and we show the low and high levels as well as the mode and the median for these elements in those specifications, just to give you an idea of what the range is. You can see in some cases the range in specification is quite broad. But the important takeaway here is there's really two groups of impurities that can have a detrimental effect on the battery. One is a group of elements that can catalyze production of hydrogen. Hydrogen can cause the valence of the electrolyte to drift and have an impact on the capacity of the battery. And we also have a number of elements that could potentially precipitate in the analyte or catholyte during charging or discharging. And the precipitates are a problem because they can block the flow paths for the electrolyte, the channels through the cell stack. That will obviously impact performance of the battery. Different cell stacks have different sensitivities to impurities. You have a number of flow fields in the cell stack, flow through, flow by, and interdigitated flow. And each one of those is going to have a different susceptibility to issues with impurities. It's not really a one-size-fits-all situation. So we've got to go through all of these elements and discuss with the battery cell stack producers as well as the electrolyte producers what's achievable and what's really important in terms of performance. Next slide. So the last meeting in Tokyo, the output of that meeting, one of the outputs was a draft specification for the electrolyte. Next slide. And I think we have identified something like 42 elements that are important to be considered in the specification. Here you see the status of the proposal at this point in time. Next slide, please. So yeah, here we have, total of 42 elements that are being looked at. And as the discussion goes forward, we'll be focusing on each one of these and trying to decide what levels should the specifications be. You'll see here there's two concentration grades, A and B. Really, the specification is developing two grades of electrolyte. One, let's call a high purity grade, and second, a technical grade of electrolyte. Again, acknowledging that different systems are going to have different susceptibility to issues with impurities. There's a need to develop two standards. Next, please. So last meeting was in Tokyo. We've seen the draft just now of what came out of that meeting. Next, please. There is another meeting now of the Joint Working Group 7 that will take place just before the Flow Battery Forum in Vienna in June 23rd. During this discussion, we're going to be going through this draft. The idea of looking at groups of impurities and a limit on a group of impurities as opposed to some specific impurities has been tabled, and I think that'll be a good point of discussion. Another issue here is, as I see, a misspelled analytical, but analytical methods and capabilities. We're talking about very, very low levels of some of these impurities, and there's a real need to understand what the analytical limitations are of the industry and also what the ability of electrolyte producers is to produce material to these low levels. The analytical side of this becomes important given the low level of impurities that we're looking at. And it's, just my guess that maybe sometime in 2026, a specification for the electrolyte will be put forward by IEC. Next, please. So that's it on the electrolyte. I know Natalia from Fraunhofer is on the line here. I don't know, Natalia, if you have any further comments. Natalia's really been central in this discussion. If you've got any comments, John, I don't know if she can jump in and make those.
Yeah, let me unmute her as an attendee. 1 second here. I can find her. Natalia, if you'd like to say anything, go ahead. Tara, we're not able to hear her, I
Yeah,
guess.
okay, no worries. If she
Sorry.
has any comments, I'm sure she'll pop them into the chat. And like I said, Fraunhofer's been central in this effort, so really appreciate their leadership in this process. Now we're going to turn and talk a little bit about vanadium market. And, sorry, Natalia?
Can you hear me now?
Yes,
Yes,
we can.
Okay. Yes. Yep. Thank you very much for the introduction.
sure. Do you have any comments, Natalia?
No, currently I'm open for the questions eventually.
Okay. Okay. Well, I think if there's any questions, those are going to be popped into the chat
Into
and
the
John
Q&A.
in the Q&A.
Okay. Yeah.
Okay. 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 Great. All right. Let's go on and talk a little bit about vanadium market. We're going to look at some data here, historical production consumption, and some forecasts going forward. Looking at vanadium production, here's our data for the last 23 years or so. We can see, dramatic increase in vanadium production over this period. Obviously, majority of the production is coming from China, but you do see other regions that are important in terms of production. Next slide. Vanadium, basically, there's three types of raw materials that are typically used to produce vanadium. One is slag coming out of steel mills processing vanadium, titanium, magnetite in China, in Russia, and one small mill in New Zealand. And that vanadium slag supplies something like 70% of vanadium today. We also have some primary vanadium ores. These are mines in South Africa and Brazil, and mines in titanium. They don't those operations, and they are quite important. And then finally, we have the secondary producers. This is recovery of vanadium from residues generated in other industrial processes. The majority of the production from secondary sources is recovery of vanadium that is coming out of the ground in oil. There is a significant amount of vanadium in oil in various parts of the world. And when that oil is either refined or burned, will generate a residue at the end of the refining process, or a boiler ash or slag from the thermal power stations where the vanadium is concentrated. And those materials can be used for vanadium extraction. We are seeing now a growth in recovery of vanadium from alumina processing. The Bayer process for processing bauxite to alumina generates a residue that will contain vanadium in many cases, and that material is being exploited more and more as we go forward. Next slide, please. So here's my projection of what we think we're going to see in terms of changes going forward. And it's important to note that in this effort, what we're looking at is the traditional markets for vanadium with some very modest growth, probably very little growth overall in steel consumption of vanadium in the coming years, given the situation with steel, particularly in China. Titanium demand will grow, but it's only about 5% of the global demand today. So even with high growth rates, the impact on the production is sorry, I got into excuse me. The production of vanadium from steel slags, again, we are looking at some growth here. All of this forecast is based on the assumption that the demand for traditional applications of vanadium is going to be relatively flat, modest growth, but we're going to see tremendous growth in demand for batteries. And so as we look at the supply side, we have to ask ourselves, how do we possibly get from where we're at now to the significant increase in production that we need to meet this surging demand for batteries? And the way that can happen is if all of the idle capacity out there that's not in production today comes online, and we have some new sources of production. So this production forecast is showing all of the idle capacity for slag production, which is primarily in China, growing. That's I think an interesting proposition given the state of the steel market right now. But in order to show a supply base that can meet the surging demand, we're making the assumption that all this idle capacity comes online. Next slide. From primary ore, really the idle capacity that's out there right now is Chinese stone coal. There's a significant amount of idle capacity out there that, again, our projection is showing that is going to come back online. And this this forecast also shows some new primary production from Australia and Kazakhstan. So, there's a number of potential new vanadium mines out there. The question of who gets to market first is a serious question, but this is one forecast. Next slide, please. Secondary vanadium production. Again, we see a large increase primarily in China, and this is largely associated with recovery of vanadium from residues generated in the Bayer process, converting bauxite to alumina. So we've seen a significant increase of that in China in the last couple of years, and I think we're going to continue to see that as well. At the same time, we've got a new vanadium production facility that will start construction later this year in Saudi Arabia, and we're expecting to see more of these secondary facilities come online. The gestation period is shorter than that of a primary vanadium mine. The capital requirements are less than what we need for a typical vanadium mine. So as we see this surge in demand, we think that some of the early movers in terms of supply are going to be these secondary sources. Next, please, John. So here's our forecast, just looking at the supply base from various raw materials. We've talked about this a bit already. Next slide. Looking at the production by country, the forecast is showing, significant increase in China and the advent of some production from Australia and Kazakhstan in the Middle East. Next slide. In terms of consumption, historically, this is the picture that we see. We see the dip that occurred in 2016 with the terrible situation of the steel industry. We saw good growth up through 2021, and consumption's waned a little bit as a result of the decrease in rebar production in China over the last few years. Next slide. So this is our forecast for consumption in flow batteries, and this is really the biggest variable out there in this discussion. What this forecast is suggesting is that demand in China is going to grow at about 45% compound annual growth rate over the next several years. And we're going to see a higher growth rate outside of China, but still the vast majority of the installations of these batteries we see occurring in China. So this is showing vanadium flow battery installations in gigawatt hours. The next slide will show what that means in terms of vanadium. We're talking about metric tons of V here. So we're talking about demand reaching almost 155,000 metric tons of V per year in 2030. And just for context, the market in 2024 in terms of consumption was about 120,000 metric tons of V. So it's essentially more than doubling demand in the next few years. Next slide. Look at this data on basis of China versus the rest of the world. And again, we see the trend continuing that we've seen since the early 2000s, where China is the predominant consumer of vanadium as well as producer. Next. Here again, we look at consumption by application. We see, somewhat stable consumption in the steel industry, growing demand from the titanium industry, but the percentage of the market is small. Chemicals is also a very small but growing segment. And then we see the light blue bar, the energy storage, particularly vanadium flow batteries, representing the preponderance of growth and demand going forward. Next, please. So here we try and roll this up and look at what's going to happen in terms of consumption from traditional markets Layer on top of that the forecast for energy storage, and then the line shows what we expect in terms of production. And again, this assumption that all of the idle capacity out there that can come online does come online, and we see some fairly significant new primary vanadium production and secondary vanadium production yields this forecast for production. And you can see that this forecast suggests that we'll have the opportunity to grow the market and meet the demand in the next few years. This forecast does show us coming up short in terms of supply relative to demand by 2029 and 2030. You can see if you look back the last few years, the production of vanadium has been above consumption, which means we've built some inventory. And if this forecast holds true, we will see production and consumption fairly in balance for the next few years. But again, that's dependent on a lot of idle capacity coming online fairly quickly. And given that combination of situations, it looks like there's excess inventory in the pipeline right now, and this balance between production and consumption going forward will dictate how quickly the quote excess inventory that's in the system gets burned off. Next, please. So this chart shows our effort at trying to look at what is the actual cash cost of producing V2O5. And what we see here is that the cash cost for most producers is relatively high compared to today's market. Next, please. Historical data on vanadium pricing. This is in warehouse Rotterdam duty not paid basis, which is kind of the standard in the Western world. We're looking at the monthly midpoint average price, nominal price. So it's not been inflated. And what we see is going back over the last 21 years, a mean of 825. The mean doesn't mean as much to me as the median, given the non-normal nature of this data. So I kind of look at that median price of 723 as a long-term non-inflated.
Terry, if you can hear me, I think we've lost your audio. Terry, are you back? We don't hear you at all. Here.
Yeah. Okay, great. So this is just a distribution chart showing the frequency of various vanadium prices over the last 21 years. And what you can see here is the current price level is at the lower end of this distribution. Again, I'll point to the median price here as more important than the mean. Given the long tail on the right here, this is a non-normal distribution, and so that skews the statistics. But on a non-inflated basis, this data is suggesting the long-term kind of average or median price of just over $7. Next chart, when we're talking about 21 years of pricing, we need to think about inflation, particularly in the last few years. It's been significant. Next slide. So if we take this same data and inflate it, we see the same pattern in terms of price spikes and price crashes, but the statistics are quite different. And in this case, we've got a median price of very close to $10 per pound of V2O5. We can look at this data, next slide, on a distribution chart again, and you can see we're really bumping along the bottom of the historical price level in the vanadium world right now. Next slide. If we want to look back over a longer period of time, we can go back. I can go back as far as 1980 and look at these prices. And in this case, if we look at the real price, we're talking again about something close to $8. So all this data kind of suggests, what a normal vanadium market price might be. And when we look at the supply-demand picture and the projection that we're going to be struggling to meet demand. If the battery demand grows along the path we're suggesting, we need to think about what that means for the vanadium market in general. Next slide. And again, we're looking at the distribution chart here for this data going back to 1980. Again, we're near the bottom of the historical price range. Next. And that's it. So I don't know, any questions, happy to answer them. Anybody who's interested in getting involved in the IEC process of developing the standard, if you don't know how to do that, let me know. I can figure out a way to put you in touch with the right people in your country. And as usual, any questions, anybody wants to send any questions by email or phone call, just reach out to me. Thanks, John.
Yeah, we're at the end of the presentation, but Terry, there are a couple of Q&A questions for you in the Q&A. If you have a moment, we